But the more dramatic example of the change of dimension comes in the following example. You imagine the space and time to be 11-dimensional, 10 space and 1 dimension. This is the corner of string theory known as M theory. And imagine taking out of those 10 dimensions of space, 2 of them to be what we call a torus, which looks like a donut-shaped object, a tiny donut, and the rest of it keep it big. But take 2 of them to look like a donut, a tiny donut, and take the donut-shaped object, this torus, shrink it to 0 size. Basically, when you shrink it to 0 size, it's like getting rid of it. So your space should look like 9-dimensional space when you look at it tiny, tiny, tiny. So the 11-dimensional theory should become 9-dimensional, right? That would be no trick here. You're just changing the shape. If you put the magnifier, it's still 11-dimensional. Well, it turns out when you do this, the theory becomes 10-dimensional, not 9-dimensional. Bizarre. That's the kind of statement I mean. The notion of dimension is not an invariant concept in string theory. Distance is not invariant. Topology is not invariant. The dimension is not invariant. We have to radically change the way we think about space and time. So even though these aspects of string theory are quite amazing, but the main aspect of string theory is understanding quantum geometry. Quantum geometry refers to trying to unify geometry with quantum mechanics. This was, after all, one of the triumphs of string theory, to try to combine these 2 pillars of physics, quantum theory and Einstein's theory of gravity, which is geometrically based theory. So what do we learn about the quantum geometric aspects of string theory? So the very first thing is that we want to understand is the notion of fundamental. Is the notion of fundamentalness invariant? Namely, when we talk about fundamental constituent like fundamental particles, whether that notion is something that everybody agrees. You say, there's an electron, this is a fundamental particle. There's a photon, that's a fundamental particle. Is that notion a duality frame invariant concept? So in fact, in particle physics, we divide the particles into 2 types, elementary and composite. By looking at this picture, you can imagine that I'm thinking of this like, for example, the nucleus of an atom made of different constituents. Each one of those constituents perhaps could be elementary, if maybe they are made of something else too, but you wouldn't think that at some point, you will have a basic object and elementary object. So the question is, does the notion of fundamental particle, fundamental entity, something that everybody agrees on? Or there could be some disagreement of what's fundamental or not. It turns out that the notion of what is fundamental even depends on the frame of reference, the duality frame. Some people might think this is fundamental and the other one is composite, and some other person will think opposite. So in fact, a nice example of this in the context of monopoles versus electrically charged matter. So magnetic monopoles, like these objects which are just a single pole of a magnet, for example, have been seen in theoretical examples of quantum systems to exist. But they are typically very massive. And so they should be viewed as kind of being made up of these more elementary constituents involving electrically charged fields. So you can have some composite combination of these electrically charged fields which behave as if they have magnetic charge. And these are the analog of the monopoles, the magnetically charged objects. So we usually view monopoles as composite, made up of these more elementary ingredients, which is why we kind of don't think we see them in experiments, because they're so massive and so big, they're hard to make. But if you change your parameters, they can shrink the center of these monopoles to begin to look like a point. And in fact, from their perspective, you can actually have a complete reversal of a description. As you shrink them, as you change your parameters so the magnetic monopoles become light, the electrically charged object becomes massive and heavy. And so when you want to describe the electrically charged objects, they can themselves be viewed as composites of these magnetically charged objects. Very bizarre. So the notion of what is fundamental or not gradually changes as you change the parameter, as this monopole shrinks to a point, it behaves like an elementary particle. And the electron, which was looking elementary, becomes fatter and fatter and looks like not an elementary particle anymore. You could say, well, at some point it was, and now it's not. Well, but there's no exact dividing line. Where do you divide it? There is no dividing line. Therefore, the notion of fundamental particle is not fundamental itself. We cannot have the notion of what is fundamental. Another example happens for strings. I told you that in the context of string theory, point particles are replaced by strings or higher dimensional objects. Well, what about those? Well, it turns out that in string theory also, we have a notion of a light string. Here I'm denoting it by a thin red string, and a very heavy string, analog of these monopoles, which are really fat, heavy guys. So by this thick yellow line. But as you change some of the parameters in the theory, the light one becomes gradually heavier, and the heavier one becomes gradually lighter, which I'm denoting here by changing the width of the string. And as you change the parameter a lot, the light one becomes really heavy, and the heavy one becomes really light. And in this corner, you can think about this other string as being composite and the other one being elementary. OK, so there is no fundamental notion of elementary string in this sense. They actually change. So there's no notion of fundamentalness here. In fact, this actually poses a big challenge for understanding quantum mechanics. You see, Feynman had a very beautiful description of quantum theory in the very geometric way of saying, if you want to talk about the probability of a particle going from a particular point at a given time, denoted here by space-time event A, going to a particular point B at a later time, what you need to do is to sum over all possible paths it can go. But in order to formulate quantum mechanics in this way, as Feynman does, you have to say what is the notion of fundamental particles. Because this formulation of quantum theory relies on summing over only fundamental particles, not composites. Otherwise, it would be redundant. You will have to choose the fundamental particles. So you say, OK, I will just choose fundamental particles. And I calculate all possible ways I can go from one to the other to describe my physics. But if you don't know what is fundamental, what do you replace this picture with? We do not have that picture yet. This is on the border of what we have understood in string theory. We have known that there is no notion of fundamental particle, but we don't know what replaces Feynman's formulation of quantum theory. This must be replaced by something else. So this has to go too. Feynman's path nickel has to be replaced by some other thing, and we don't know yet. Now we're getting to even more basic things. Is the notion of quantum itself. What is quantum? Is that notion duality invariant concept? Do everybody agree that this thing is a quantum effect, or this thing is not a quantum effect? Is that notion duality invariant statement? So I told you quantum mechanics basically comes about by starting with something which we call the classical system, the usual system that we usually think about, but we quantize it, which means that it basically introduces a fuzziness. So for example, when I was describing the electron inside the atom, the position of the electron became fuzzy. So there's this fuzziness, which is quantum. So you could say, aha, if I look at the inside the atom, that fuzziness is a quantum effect, right? It's not point-like, it was just fuzzy. So you can distinguish the fact that there is some quantum effect. So in that case, it looks like an invariant concept. What is this fuzziness is the quantum effect. So I draw this by this picture, so you can have, I'm just drawing a shape of something like, say, the path of the electron or something. So classically, it could have some particular shape, very specific point going in the very specific trajectory. Quantum theory says, no, it's not exactly one point, it's actually fuzzy. So we can say, aha, this fuzz around the straight line or very sharp line is because of quantum phenomena, which is this, here I have denoted by the parameter, the famous Planck's constant, which denotes how much effect of quantum mechanics you have. You can dial that to make the quantum effect bigger or smaller. So you can say, OK, there's a classical piece, and then there's a quantum part. OK, it looks like an invariant concept. it turns out that even that, the notion of what is a quantum effect is not an invariant concept. How could that be? It's so obvious. You have this thing that gets fuzzy. How could that not be an invariant concept? Well, what happens is roughly like this. You start with something which you thought is classical, and it becomes fuzzy. But if you take an extreme fuzziness, it becomes again looking classical, but a different classical system. So the quantum mechanics is a way to go from quantum mechanics dials from one classical picture to another one as you dial this fuzziness. So which one is more fundamental, this classical or that one? You pick. So the notion of quantum effect is not fundamental. So the pillars of physics are falling one by one down. I'm telling you what is not going to stay. The notion of quantum versus classical is not fundamental. Does quantum matter exist in higher dimensions? Well, we know that in three-dimensional space and one time, there's matter, electron, quarks, this and that. Do they exist in higher dimensions? Of course, I have to clarify the question. I have already told you string theory lives in higher dimensions. So of course, since string theory is made of things, so there is some matter in higher dimensions. So what I mean here more precisely is whether there are interesting quantum systems, interesting interactions like the kind of things we see inside the nuclei, the confining quarks through these strong forces inside the nuclei. Are there interesting quantum matter systems in higher dimension? That's not obvious. And in fact, there are heuristic arguments that says that in 3+1 dimensions, the only way you can have interesting matter systems made of particles. And that's, in other words, if you want to have things made of particles, you only can go up to 3+1, no higher. But in string theory, it turns out you can go higher, and it turns out you can go all the way up to 6 dimensions. And we have discovered theories of matter, interesting matter, similar to things that could be very exciting, like the nuclei and so on we're familiar with, if you go all the way up to 6 dimensions. So up to 6 dimensions, we can have interesting matter. What kind of matter can you get from them? What kind of nuclei or things can there be? What kind of periodic tables would that give rise to? Very interesting. So these are the new things we have learned, but we have also learned these are the basic entities for these theories will be these, instead of particles, they are made of tensionless strings, the strings which are very light. So these are new theories that physicists are intensely working on to try to unravel the analog of these new kinds of matter systems in these higher dimensions. Very enigmatic theories. And we are in the early days of understanding these theories, we have very little computational tools, and we are building up computational tools to try to address some of the questions we would like to answer.